Welcome to Chem 1. Today we're going to discuss naming inorganic compounds. This material is found in your book in Chapter 2, Chemistry, the Central Science, but it's presented here a little differently than your textbook does. I thought this might be helpful to you to try to get a handle on this important task of learning how to name inorganic compounds. So before we even do any discussion about what the atom is and the theory of the atom, let's discuss how these elements combine to form compounds. So there are a few essential definitions. An element is a material made of only one kind of atom. For example, pure gold is made of only gold atoms. The atom is the fundamental unit of an element. So when we talk about the word element, we're usually referring to macroscopic quantities, the amount that we could hold in our hand. When we use the term atom, usually we're discussing these submicroscopic particles that are the simplest building block of each element. The fundamental unit of an element is indicated by its elemental formula. For elements, where the fundamental units are individual atoms, the formula is simply the chemical symbol. For example, the symbol for gold is AU. That's capital A, small lowercase u. That's not Auburn University, it's AU. Notice that the first letter is always capitalized. So for example, the symbol for hydrogen is capital H, not lowercase h. The symbol for helium, element number 2 on the periodic table, is capital H lowercase e. It's not capital H capital E. It's not lowercase h lowercase e. So the first letter is capitalized, but the second letter is never capitalized. And this is important, and you'll see why in just a moment. Now, this is easy. The chemical symbol, which is the elemental formula for an element, is just the first letter or the first two letters of the element. Having said that, there are 11 elements where that doesn't seem to be the case, but it actually is if you know what language they were using when they first named this element. For example, the symbol for antimony is not A or AN, it's SB from the Latin word stibium. And the same is true for these other elements that are on this list: copper, gold, iron, lead, mercury, potassium, silver, sodium, tin, and tungsten. They're named after the Latin name for that element. These were some of the earliest elements discovered, and at that time I suppose they thought that Latin was going to be the universal language. Consequently, it was determined that English would be, so most of the elements that you'll learn symbols for come from the English word for that element, not the Latin word. Now, you don't need to know these Latin words. I just thought I'd throw this in so you'd have some understanding of why, for example, sodium is Na, not S or SO. Now, I'm going to give you a quiz on elements 1 through 56 on the periodic table soon. I'll give you the name and you'll provide the symbols. It's an easy thing to do. Just review the first 56 elements all the way down to barium, and I'll give you the name on a sheet of paper and you will provide the symbol. Remember, the first letter has to be capitalized, the second letter has to be lowercase. I'll mark it wrong if they're both caps. I know some people write in all caps, but you can't do that in chemistry. So here's the periodic table. And like I said, the elements are numbered starting up here in the upper left-hand corner, and as you move from left to right, they go 1, 2, 3, 4, 5, 6, and so forth, all the way down to barium, which is element 56. And that's as far. We're only going to learn the symbols for the elements of 1 through 56. Now, everything around you is made up of atoms. The number of different kinds of atoms is surprisingly small, just a little over 100. So all the great variety of substances come from many ways. Just this few number of atoms can be combined, just like the 26 letters of the alphabet make up all the words in our dictionary. So as we've mentioned, gold is made from gold atoms, nitrogen from nitrogen atoms, carbon from carbon atoms, and the way we identify these on paper is with the symbols. AU for gold, N for nitrogen, C for carbon. Now, when atoms of different elements bond to one another, they form a compound. For example, sodium atoms and chlorine atoms combine to make sodium chloride, which is table salt. So these elements combine to form compounds. Hydrogen atoms and nitrogen atoms combine to make ammonia. Ammonia is a common household cleaner. Ammonia is the common name. Sometimes in textbooks we see these representations of what we think atoms might look like when they combine to form compounds. These are just artists' representations of what they think it might look like. Sodium atoms and chlorine atoms here in this crystal lattice. And here we have hydrogen atoms, the white balls, and the nitrogen atoms, the blue balls, combined to make the ammonia molecule. So a compound is a substance consisting of atoms of different elements. One thing to keep in mind is that when elements combine to form compounds, the properties of this compound are uniquely different from the elements that combine to form the compound. For example, sodium metal is a soft silvery metal that's explosive if left out in the air or in contact with water. Chlorine gas is a green poisonous gas, and yet if you combine this explosive metal with this poisonous gas, you get sodium chloride, which is salt that we use to sprinkle on our food, which is not toxic. So a reactive metal and a toxic gas form salt. The properties of salt are unique from the properties of the elements that it's made from. So that's an important principle to keep tucked away in the back of your mind, that compounds have properties uniquely different from the elements from which they're made. Now, when these elements combine to form compounds, we have a formula that's used to show the proportion by which elements combine to form a compound. So a compound is represented by its chemical formula, in which the symbols for the elements are written together. For example, sodium chloride has the symbol for the compound NaCl. Ammonia, NH3, water, H2O. Remember how we said the first letter had to be capitalized and the second letter of the symbol for the element had to be lowercase? Here's the reason why. You can see when you look at the formula for the compound sodium chloride, there are only two capital letters, the N of the Na and the C of the Cl. So at a glance you can see that there are two capital letters, and therefore there are two elements in this compound. And that's why we only capitalize the first letter, so that we can at a glance see how many elements are in a compound. In ammonia, there's two capital letters, so there's two elements. In water, H2O, there's two capital letters, so there's two elements. Now, the International Union for Pure and Applied Chemistry, IUPAC is their acronym, has developed a system to, in a systematic way, name compounds, and that's what we're going to use primarily. The chemical identity of a compound can often be discovered through this systematic name. Now, while we're not going to learn all the rules that the IUPAC has put out there, there are some guidelines that we're going to learn that will help you. Again, this is not exactly the way it's presented in your book, but I think it'll be helpful. We're going to talk about how metals combine with nonmetals, how metals with multiple oxidation numbers combine with nonmetals, how metals or other elements, nonmetals, combine with polyatomic ions perhaps, and how nonmetals combine with nonmetals. Now, of course, you got this PowerPoint and this video, but you might want to take some notes. As I mentioned, this material is not the material from your book. So as we look at the periodic table and its general shape, we note that sodium, for example, is on the far left-hand side of the periodic table, where chlorine is on the far right-hand side. When sodium and chlorine combine to form a compound, we call that compound sodium chloride, and it has the formula NaCl. But you might wonder, how do we do that? So on the left-hand side of the periodic table, everything on the left-hand side are generally referred to as metals. Now there's a stair-step line on the periodic table that goes right through this region, And everything to the left of that stair-step line are known as metals, and everything to the right of that stair-step line are known as nonmetals. So if we take a metal, that is an element from the left-hand side of the periodic table, that's sodium, and combine with a nonmetal, a chlorine, that's an element from the right-hand side of the periodic table, that's one of the simplest kinds of compounds that can form, a metal plus a nonmetal. And so the way we name this is we name the metal and then we name the nonmetal, except we change the ending of the word for the nonmetal to IDE. So when sodium combines with chlorine, we don't call it sodium chlorine, we call it sodium chloride. When we go to write the formula for this metal that's combined with a nonmetal, we follow these steps. We write the symbols for the two elements. That's why I'm having you learn these symbols. Na for sodium, Cl for chlorine. Then we write the oxidation numbers. Now, I know you don't know probably what oxidation numbers are yet, but that's okay. We'll talk about what they are later, but right now, all you need to know is that we find the oxidation numbers on the periodic table. It's the number that's right above the symbol for the element. And the metals all have positive oxidation numbers, and the nonmetals have negative oxidation numbers. Now, sometimes the nonmetals will have more than one possibility. And for Chem 1, for a nonmetal, we're always going to pick the first oxidation number listed and make it negative. So for chlorine, you'll notice on the periodic table, it has plus or minus 1, 3, 5, and 7. So we would always make the oxidation number, the first one, 1, and make it negative, negative 1. Now, if those two oxidation numbers, that is the oxidation number for the metal and the oxidation number for the nonmetal, add up to 0, then we're finished and the formula is complete. However, if they don't add up to 0, then we're going to cross them. And this is what I mean by that. So, for example, NaCl, those are the two symbols, Na for sodium and Cl for chlorine. Those are the oxidation numbers that we found on our periodic table. And because plus 1, when you combine it with negative 1, adds up to 0, we're finished. The formula is NaCl. But let's suppose we had aluminum combining with chlorine. The oxidation number for aluminum is plus 3, and chlorine, again, is negative 1. These do not add up to 0, so the 3 moves, we cross it and take it down next to the Cl, and the 1 we put down next to the Al. However, we usually don't write the 1s as a subscript. Now in Chem 1, you can write the 1 if you want. I'm not going to mark it wrong if you write the 1. But just by having the symbol for aluminum listed Al, it's assumed that there's 1 already there. We usually only write the subscripts when it's greater than 1. Now let's look at aluminum combining with oxygen. The oxidation numbers for aluminum and oxygen are plus 3 and minus 2. They do not add up to 0, so we cross them, and this is what we come up with, Al2O3. A second possibility would be a metal with more than one oxidation number combining with a nonmetal. Now, don't be confused. We said the nonmetals might have more than one oxidation number. As a matter of fact, they often will. And we would always pick the first one and make it negative. However, when a metal has more than one oxidation number, we're not always able to do that because we may need to use either or of the oxidation numbers that are listed for the metal. So we have to have a way for having compounds where metals might have several oxidation numbers. For example, if we want to write the name of a compound where iron has a plus 3 oxidation number and it combines with oxygen, this is how we write the name. So we name the metal iron. We name the nonmetal. Again, we change the ending to IDE like we did before. So it'd be iron oxide. Only iron can have a plus 3 oxidation number or a plus 2 oxidation number. So we're going to add a Roman numeral next to the word iron, Roman numeral 3, to indicate the oxidation number of iron. In this case is plus 3. So we'd say iron plus oxygen is iron oxide, but the complete name here would be iron, Roman numeral 3, oxide, indicating that iron's oxidation number is Roman numeral 3. is 3. Now, this name then has a lot of information in it. Uh, if you were to try to write the formula using the name iron oxide alone, you wouldn't know whether to use iron as a +2 or iron as a +3. But when we have the full name, iron Roman numeral 3 oxide, and the way we say this is just iron 3 oxide, then we know to use 3 as the oxidation number. This does not mean use the third oxidation number listed. It means literally use 3 as the oxidation number for that metal, iron. Now, let's say we want then to understand all the ways that we might name compounds where a metal has more than one oxidation number. A rather outdated system, but I only mention it because you still see it from time to time, is to use the Latin name for the metal. You use the regular name for the nonmetal with its ending changed to IDE, and then you add an ending to the Latin word for the metal, adding an ending OUS if it's the lower of the two oxidation numbers, or IC if it's the higher of the oxidation number. So for example, if we were talking about iron, iron with the lower oxidation number, the +2 would be ferrum. And if we had iron 2 oxide, where iron has a +2 oxidation number, we would call this ferrum oxide. If it was iron with a +3 oxidation number, the higher of the two, we would call it ferric oxide. Now, I'm not gonna spend much time on that because we will more than likely use the Roman numeral way of naming compounds when the metal has more than one oxidation number more often, because that's a systematic way. It gives us more information and it's not so antiquated. But you'll see that from time to time where you have the ending of the metal and that's us or ic, and us just means to use the lower oxidation number and ic means to use the higher oxidation number. Now, how do we write the formula for these compounds where the metal has more than one oxidation number? Well, the same way that we did when it was just a simple metal with a nonmetal. We write the symbols, we write the oxidation numbers, and if they add up to 0, we're finished, but if they don't, then we cross them. For example, let's say we have iron with a +3 oxidation number and oxygen with its -2. These oxidation numbers do not add up to 0, so we cross them, and we have Fe2O3 as the formula for iron 3 oxide. If we were talking about iron with the +2, you notice that the +2 oxidation number for iron adds up to 0 when you combine it with the -2 oxidation number of oxygen. And so that formula is finished. We would not write it Fe2O2. We would just write FeO. Now, in this class, if you were to write it this way, I probably would not mark that wrong, but technically it should just be FeO because +2 and -2 add up to 0. Now, a third class of compounds that you'll see often is when we have a metal that combines with a polyatomic ion, something like carbonate. You have a list of polyatomic ions that I have given you or will give you soon. So if we had the metal sodium combining with the polyatomic ion carbonate, the way we would name this is we'd name the metal, we would name the polyatomic ion, and then we would be finished. So for example, sodium plus carbonate, the name is sodium carbonate. If we wanted to write the formula for sodium carbonate, we would do it the same way that we've been doing. We'd write the symbols, we'd write the oxidation numbers, and if the oxidation numbers add up to 0, we're finished. If they do not add up to 0, then we cross the oxidation numbers. So sodium carbonate. Na is the symbol for sodium. Carbonate has the symbol C, capital O, with subscript of 3. CO3 is the symbol for carbonate. You have this on your list of polyatomic ions. Sodium has an oxidation number of +1. The charge on carbonate is -2. They do not add up to 0, so we cross them. The 2 comes here, and the 1 would come over here, but like I mentioned before, we usually don't write the 1s as a subscript. Now, if we had aluminum combining with carbonate, aluminum has the oxidation number, and carbonate has its -2 charge. we're going to have to cross these because they do not add up to 0. So we bring the 2 down next to aluminum, and the 3 we bring down next to the carbonate. We put carbonate in parentheses so the 3 can come outside of the parentheses that encloses carbonate, so that it looks like aluminum carbonate. That is 3 carbonates, 2 aluminums. Now, there is a class of compounds where 2 nonmetals combine, and you're very familiar with these. You've heard about these. You may not have known that there were 2 nonmetals, but now you do. For example, carbon dioxide or carbon tetrachloride. And the way we name these is a little different. We name the nonmetals with prefixes that describe how many atoms are present in the compound. For example, carbon dioxide, that is the name carbon dioxide, describes a compound consisting of 2 nonmetals, 1 carbon and 2 oxygens, CO2. Now, to be able to do this, we have to learn these prefixes for the numbers 1 through 10, these Greek prefixes. So the prefix for 1 is mono, for 2 is di, not bi. If a chemist had to name the bicycle, he would have called it a dicycle. Tris is the prefix for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. You're just going to have to memorize these chemical prefixes. So, if we wanted to describe, for example, carbon monoxide, or the formula from 2 nonmetals where there's 1 carbon and 1 oxygen, we would name it carbon monoxide. I'm not sure why, no one's ever explained it to me, but for some reason we don't use the prefix mono with the first nonmetal, only with the second nonmetal. So when we have 1 carbon and 1 oxygen, whereas you might be tempted to call it monocarbon monoxide, we actually in practice call it carbon monoxide. We don't use mono for the first nonmetal in the compound. Again, in Chem 1, if you were to call it monocarbon monoxide, I would not mark it wrong, but usually we'd only use mono for the second nonmetal. So let's say that then we want to write the formula. Well, this is easy because the name in this case is a dead giveaway. Whenever you see these Greek prefixes, it describes the formula to you. So we write the symbols and then we write the subscripts based on those prefixes that are in the name. For example, if we had the compound carbon monoxide, we would know that the formula is CO. I'm sorry, carbon dioxide would be CO2. Carbon monoxide would be CO. Those formulas we can write those easily once we have the name, because the name describes how many of which elements are in these chemical compounds. Now, after we've learned these rules, what we know is that there are still in the world common names that have caught on. For example, when hydrogen combines with oxygen, technically and systematically we would name it hydrogen oxide, but nobody calls it hydrogen oxide. Everybody calls it water. H2O2, everyone calls this hydrogen peroxide. These are common names that have caught on. And so if there's a common name, we will default to that one. Here's a little quiz for you. So what would the name of the compound with the formula CBr4 be? Notice that these are 2 nonmetals, both of them to the right of the stair step, 1 carbon and 4 bromines. What if we wanted to name that? Would it be Cro-Bro4? I don't think so. CBr4? I don't think so. Carbon bromide or carbon tetrabromide? It would be carbon tetrabromide. It's a compound made from 2 nonmetals, carbon and 4 bromines, carbon tetrabromide. When you see that prefix tetra, you know that that's your clue that it's 2 nonmetals combined to form a compound, carbon tetrabromide, CBr4. Well, that's a quick description of how to name chemical compounds. A little different from how it's described in your textbook, but hopefully it will be helpful to you to think of chemical compounds being made from a metal and a nonmetal, or a metal with more than one oxidation number plus a nonmetal, or perhaps a metal plus a polyatomic ion, or perhaps two nonmetals combining to form an inorganic compound.